Hello. Welcome to the Zero Knowledge Implementation session. And in this session, we'll have two talks. The first one will be arkworks, a Rust ecosystem for programming ZK SNARKs. And Pratish is going to give the talk. Okay. Can we have the slides?
Okay, fantastic. Okay, I think everybody can hear me. All right, hi everyone. I'm Pratyush. It's fantastic to be here. And today I'm going to talk about arkworks, which is a Rust ecosystem for ZK SNARKs that we've been developing over the past 3-4 years. And this is a joint effort of a lot of folks at Berkeley and elsewhere. Okay, let's get started. So before we can talk about implementing and programming with ZK SNARKs, we first have to figure out what these ZK SNARKs are. All right? So ZK SNARKs are a very special kind of zero-knowledge proof system where, in a standard way, you have a prover who wants to convince the verifier that some statement is true without revealing information about why the statement is true. The special properties that ZK SNARKs offer are two. Right? The first is standard zero knowledge, which hides information about the prover's secret input. And the second one is succinctness, which means that the verifier's running time is much less than the size of the statement. So even if a computation takes a year to perform, the prover's proof can be checked in just a few milliseconds. Okay? Now this seems kind of mind-boggling at first, but trust me, these things exist. And these zero knowledge and succinctness properties have led to ZK SNARKs having lots of applications in a number of domains. These applications include things like private transactions, private and scalable smart contract systems, decentralized multiplayer hidden information games, and many more. Anonymous credentials, proofs of security vulnerabilities, coercion-resistant voting, and more. Okay? So this is clearly an exciting primitive, right? And people have been using it to develop applications. But how do they actually go about developing these applications? And what are the various steps? Well, the first thing you have to do is figure out how to express your computation in a language that the ZK SNARK understands. Now, unfortunately for us, SNARKs don't natively understand C or Python, right? What they understand instead is what's called an algebraic constraint system. Now, you don't really want to write your computation directly in the algebraic constraint system. And thankfully for us, people have developed a number of languages and frameworks which allow you to express your computation in a high-level manner. And that high-level computation then gets compiled down to constraint systems behind your back. Okay? So people have done this work, but there's a lot of libraries. So you have to figure out which one matches your use case and pick one, and then express your computation in that framework. But after you do this, your job is not done. You have to figure out which ZK SNARK you want to use, which one matches your use case. Do you want extremely fast provers? Do you want really small proof size? Sort of what is your constraint arising from your application, right? And there's a vast landscape of ZK SNARKs which offer different trade-offs along these dimensions, right? So you have to get yourself acquainted with these properties and these trade-offs and figure out which SNARK to pick. All right, okay, assuming you do that, right, you're still not done because all of these ZK SNARKs rely on algebraic objects such as finite fields, elliptic curves, pairing-friendly elliptic curves, and more, right? And again, there's many choices to be made here. So ideally, yeah, you have to figure out whether you want a particular finite field or a particular pairing-friendly elliptic curve. And again, then you're still not done because you have to either implement or find an optimized implementation because these ZK SNARKs have enormous overhead compared to sort of running your computation normally, like orders of magnitude. So you really want to pick a very optimized implementation for your application. Otherwise, it's going to be really slow. Okay, and there's again lots of choices for optimization here. Okay, so all of this seems like a lot of work, right? And something that you don't want to do over and over again. You want to just have some common libraries that everybody uses, and then you can just pick and choose what you want from that set. Well, unfortunately for us, people don't actually do that today. What they instead do is develop many different libraries in various languages with different kinds of proof system and different kinds of constraint programming frameworks. And it's just like a big mess of incompatible stuff. Now, there's very good reasons to actually do this, right? The people implementing this are very smart, and they have actual business reasons and protocol reasons to do this, including things like optimization. It's much easier to optimize your code for your application if you control it fully, right? There's new techniques coming out every few months, so you actually want to have control over your code to implement these new algorithms and techniques. You want to be able to integrate your code, your ZK SNARK code into your existing code base, which again is easier if you control the code base from top to bottom, right? So there's a number of reasons to do this, and this is why people have been developing these libraries. But it comes with its drawbacks, right? You waste a ton of re-implementation effort across the community. The same protocols that might be implemented in all of these libraries. Optimizations are then scattered across these libraries, right? You might have one particularly efficient multiscalar multiplication algorithm in one of these libraries, and then a very efficient pairing algorithm in another one. By scattering effort across libraries, upgrading your protocol becomes difficult. You might be stuck with a very old SNARK just because you don't have the manpower to analyze and implement a new one. And finally, very importantly, auditing and bug fixing efforts of the community are sort of distributed now across all of these libraries, instead of the attention being concentrated on one very well vetted code base. Okay, so there are these problems. So let's see how we can actually try to resolve these issues and maybe have the community converge to a single sort of set of libraries. So what we want to do is to make it really low friction to use this sort of community standard library. How do we do that? By designing your libraries in a modular way, which would allow users to pick and choose whatever parts of the ZK SNARK stack they want to use. So if they want to use just the elliptic curves from the common libraries, they can do that. If they want to use the proof systems, they can do that, right? You want it to be ergonomic to do this, so it should be really easy to do this correct secure by default thing, right? You don't want to end up with insecure protocols, and it should be easy to integrate these into existing code bases. And finally, you don't want to sacrifice efficiency, right? These ZK SNARKs are super expensive, so you want it to be easy to get performance that matches the best hand-tuned implementations. All right, so these are all like lofty goals, and this is exactly what we try to achieve in arkworks. So we set a high bar. And in particular, what we try to construct is a set of modular, ergonomic, efficient libraries that together comprise a Rust ecosystem for programming with ZK SNARKs. We achieve these properties by leveraging, for example, for modularity, by leveraging the Rust type system to abstract away details, irrelevant details at a particular level of the stack, and offer instead reusable interfaces that folks can use to construct generic implementations. I'll explain what this means in a little bit more detail in just a bit. Again, from an ergonomics perspective, we tried to leverage the Rust type system to encapsulate implementation details, again, behind these generic reusable interfaces, and leverage Rust's strong cross-compilation and FFI properties to allow interfacing with existing code-based languages. Finally, from an efficiency perspective, in arkworks, we try to offer state-of-the-art assembly and intrinsic-based implementations of field and curve arithmetic, which would allow, and also to allow folks to sort of poke through the various abstraction layers and implement curve-specific optimizations if they need to. So this would allow you to really sort of eke out the last bit of performance if your application requires it. Okay, so that's arkworks at a high level. How do we actually achieve these properties? By abstraction. Okay, so that's the name of the game in arkworks. In more detail, we sort of we figure out the various components of ZK-SNARK programming that are irrelevant at various sort of as you go up the stack, and we offer these abstract interfaces between each layer of the stack. So starting with algebra, we offer generic implementations of finite field, elliptic curve, polynomial arithmetic, and hide all of these behind these generic interfaces for the same. Then we use these generic interfaces to provide first generic, there's a lot of generic in this slide. These high-level interfaces for ZK-SNARK and constraint system programming, and instantiate these interfaces with concrete ZK-SNARK such as Gross16, Marlin, not on this slide and not from us, but other people, things like Planck and so on. And then we hide all of that complexity behind our generic interface and use this to construct gadgets or constraints for popular computations such as cryptographic primitives, things like unsigned integers, finite field arithmetic, elliptic curve arithmetic inside ZK-SNARKs. And this is relatively non-trivial to do because the cost model of ZK-SNARKs is different from your normal computation. Okay, and together sort of all of this comprises a generic SNARK application development framework, which we use to construct applications such as proof carrying data, which is, you can think of proof recursion on steroids, and private smart contracts and more. Okay? All right. So let's see how each of these layers of the stack achieves our goals of modularity, efficiency, and ergonomics, starting with the lowest level, algebra. Okay, at the algebra level, so just recall what I mean by algebra here is things like finite field arithmetic, elliptic curve, polynomial arithmetic, and so on. So at this layer, if you're a person who's implementing finite fields or elliptic curves, what you want, the things that you want are that it should be easy to implement new fields and new curves, right? So let's say you found a very efficient elliptic curve. You want it to be easy to implement that and benchmark, other proof systems with your new curve. Okay, without sacrificing performance, you still want, very high performance, which matches, which is equal to what you would have gotten if you wrote it from scratch, optimized for your curve. Okay, and we want to do this without duplicating effort. We don't want to have to implement, short Weierstrass, point addition again and again and again. All right. So let's see how we can do this by focusing on the particular example of implementing an elliptic curve. So to do this, we have to first implement the associated base field and scalar fields, and then implement the curve itself, which involves specifying the curve equation coefficients and the cofactor and the subgroup generators. Okay. For the BN254 curve, this is what it looks like in arkworks, right? So in 10 lines, you're able to specify the associated fields. So this takes inspiration and builds upon a prior API in the Bellman ecosystem. But yeah, as you can see, in these 10 lines, we've implemented finite field end-to-end, right? And this will match, as we'll see in a bit, sort of the best hand-tuned performance. Okay? So this is our field. What about the curve? This is also very simple. In, again, just 10 lines of code, you're able to specify your curve entirely. Just specify the coefficients, specify the cofactor, and specify the generator. You're done. Okay? So let's say, and in arkworks, we offer generic implementations of short Weierstrass and twisted Edwards curves, which covers, I think, most curves used in practice. So for all of these curves, you just do these 4 things, and now you have your efficient curve implementation ready to go. Okay? And we've taken advantage of this simplicity and low-effort implementation to provide implementations of a variety of curves that are used in industries such as BLS 12381, BN254, the pasta cycle of curves, BLS 1377, and more. Okay? All of this, again, just requires basically 20 lines of code to implement each of these curves. Okay? All right. So now we have a lot of these curves, right? Can we actually use them in an interchangeable manner throughout higher level protocols like SNARKs or signatures and so on? And the answer is yes. For example, let's say you're using the Gross16 ZK SNARK. with the BN254 curve, but you've heard recently that the BN254 curve doesn't meet your 128-bit security goals, right? So you want to switch to the BLS12381 curve. All you have to do is change one type parameter, and now your protocol is upgraded and is secure again. Of course, this requires more effort in practice, but for the purpose of this talk, it looks nice, right? Similarly, for signatures, right, you want to switch curves. You're just changing one type parameter, and this is the case for basically every primitive in the arkworks ecosystem. Hashes, commitments, everything, you just change one type parameter, and now you switch to whatever curve you want. Okay, and to achieve all of these modularity and ergonomics goals, we don't sacrifice performance. Rather, in many cases, we match or even outperform specialized hard-coded implementations which focus just on one particular curve, such as BLS12381. So these are slightly older numbers, but I think they should still be correct. But focusing on the BLS12381 curve, what we find is that compared to Bellman, or specifically the BLS12381 crate in Bellman, which implements just BLS12381 curve, and compared to so I guess these are two extremes. One is pure, safe Rust, and the other one is MCL, which is a state-of-the-art pairing library, which does very fancy, scary tricks, things like dynamic code generation, to achieve very fantastic performance. We sort of end up somewhere in the middle. We achieve performance better than Bellman on basically every metric, and sometimes we even beat MCL, right? And this is using very minimal unsafe code, maybe a little bit of assembly, and that's it, right? And this assembly is not specialized to BLS12381. It can be used for BLS12377, for BN254, whatever curve you have in mind. Okay. So I think this is personally pretty impressive. It took a lot of effort to get here from a lot of people. But there's still actually a lot more room for optimization here. Okay. All right, so that sort of concludes the algebra layer of the stack, right? I've shown how to achieve our modularity, efficiency, and ergonomics goals. So let's move on to the next layer in the stack, which is constraint system programming, right? And SNARK, no, sorry, that's the next level. This is SNARK development. Okay, so if you're a SNARK developer, like you've gone out, written your fantastic new paper, developing the next Plonk, Marlin, Sonic hybrid, or whatever, right? You want to implement it and compare its performance on real constraint systems against the existing state-of-the-art, right? How do you do that? What you care about here is not details about your low-level elliptic curve, how it's implemented, nor about how the constraints are generated. You just care about your SNARK prover, verifier, setup algorithms, right? So what you want here is that your performance should be good, but also that the implementation should follow closely from the math, right? You're not maybe the most advanced programmer, so you know how to do math, you don't know how to maybe write the most optimized code. So you should end up in sort of this valley of happiness where the default is the thing which looks like your math is actually the performant thing, right? And furthermore, it should be modular so that you can sort of easily switch out. You don't want to have to rewrite your benchmarks over and over again for the different curves, right? For the different SNARKs. You want to be able to just write your benchmarks once and then reuse those across all of the SNARKs that you're benchmarking against. Okay. So on this latter front, again, we're able to switch proof systems very easily because we have this generic SNARK interface. So let's say you started off with Groth 16, you really like its performance, but then you realize it doesn't offer simulation extractability. So you move to Groth Malheur 17, right? But then you realize, oh, well, I don't actually like this circuit-specific trusted setup, so you want to move to something like Marlin or Plonk. All of this can be done, again, just by switching one type parameter in your code base. Of course, again, in practice, you have more work to do. But from a prototyping perspective, it's as easy as changing this one type parameter. And later, maybe you realize that you don't like the trusted setup of the KCG10 polynomial commitment at all. You can, again, just directly switch the polynomial commitment to an inner product argument-based one and get trustless setup, right? All of this is very helpful from personal experience. when you're benchmarking and prototyping your protocol. Okay, all right. So that's from the modularity perspective. From the ergonomics perspective, as I said, the goal is that we want our actual code to map very closely to our pseudocode, right? This helps auditing, it helps bug fixing, and generally makes life simpler. So let's take the example of the Groth16 verifier algorithm. And what we see is that it consists of 2 steps. The first one does the multiscalar multiplication, and the second does some pairing products. The code looks almost exactly like the pseudocode. So we do some multiscalar multiplication, and then for this pairing product, we literally just call the pairing product algorithm, and this is it. This is, in these 10 lines, the Groth16 verifier algorithm, and you can see how it maps to the actual pseudocode very clearly, right? Okay, so sort of that wraps up the SNARK development stuff. You can see, hopefully I've convinced you that it's actually ergonomic and fairly flexible in terms of modularity. So let's quickly go over how ergonomic our constraint system writing framework is. Okay. So remember, the goal here is to try to avoid writing algebraic constraints directly, right? That's painful, error-prone, and just asking for bad things to happen to you. So thankfully, there's a number of high-level approaches to programming, to expressing your computation in constraints, but balancing performance and ergonomics here is tricky, right? Maybe you have a high-level language which doesn't expose things like non-determinism, so you can't get the best possible performance out of your proof system. So what we want to do here is to achieve good ergonomics without sacrificing performance, right? And sort of the key thing here is that there's been a lot of work on extracting the maximum performance while writing constraint systems, but it's not really been ergonomic at all, in the sense that this is what it looks like compared to the native code. So on the top, we have Karatsuba multiplication, and this is something from libsnark, where there's almost no way to actually map what's going on in the actual algorithm to the constraints, right? So what we try to do in arkworks is try to really make it as close as possible to the native code, and we were, I think, in my opinion, very successful, right? So this second snippet of code will give you a bunch of constraints for doing Karatsuba multiplication inside your ZK SNARK. And yeah, basically all of our constraint systems look very similar to this. All right, so that wraps up, I guess, my high-level overview of how we achieve modularity, efficiency, and ergonomics at the various levels of the arkworks stack. And the question is, I've talked a lot over the, I guess, past 20-ish minutes, but has any of this actually been useful, right? And the answer is thankfully yes. In the past 2-3 years, we've been able to get a lot of folks to adopt and use arkworks to implement their ZK SNARK protocols as well as other cryptographic primitives. And a number of academic papers have also used arkworks libraries to implement and benchmark their proof systems, right? So this is, in my opinion, the academic stuff is particularly important because a lot of academic papers, because the existing code bases are difficult to use, they just don't implement their libraries and just offer asymptotic guarantees. So by offering a pathway to authors to implement and get reasonable performance for their proof systems, I think it's very exciting. Okay, and this is, all of this has been the result of a lot of work by, I guess, 60+ contributors, both at Berkeley as well as elsewhere. If I missed somebody, please, I'm sorry. I finished this at like 9 a.m. after not sleeping tonight, or yesterday night, whatever. But yeah, there's been a lot of hard work put in by a lot of folks over the past 2-3 years to implement and get to where we are. Okay, so yeah, that sort of wraps up my talk. Thank you everyone for listening. If you want to get involved, there's a number of avenues to do that.
Come to the mic to ask your questions.
Thanks for the talk. So I've found, that Rust trace system is really, really good for like generically expressing crypto stuff, but there are some features like say const generics that aren't like quite where they need to be for some things. So I'm curious, are there any like known to be coming language features or just language features that you'd like to have that you think would make your like traits or your APIs a lot better?
Oh yeah, definitely. All of the stuff around const functions and const generics. There's a lot of stuff on the roadmap which would make a lot of this stuff more ergonomic. Like we would be able to get rid of a bunch of macros, things like that. And it would make, again, that, for example, the algebra code even simpler. You wouldn't even need that proc macro, for example. Yeah, other than sort of the const stuff, yeah, maybe more stabilization of intrinsics and some more, I guess, inline assembly support. As more stuff gets stabilized, that would also make our lives easier.
Thank you.
Huh?
Oh.
Yeah, parts of it, like the const expression stuff, is not stable yet.
We have some questions on the chat, so I'm just gonna read them for you. So Victor Graf is asking, how much can you do in arkworks to prevent people from combining components in ways that are insecure?
I mean, if people really want to do something, they can do it. But I think, I mean, it's, for example, things that we do is that our sort of curve interfaces, they by default only allow you to construct prime order, I guess, group elements. You can't construct things which are in like a low order subgroup or something like that. So that eliminates one class of bugs. Yeah, I think it depends very much on the specific use case. It's a very high level question, but I'd be happy to answer more in detail, maybe offline somehow.
Sure, yeah. You can use Julep to clarify or interact with Victor. And the second question is from Alexandre Yamayako. This looks great. 2 questions. Has arkworks been independently audited? Out of all of the independent implementations that you've listed in your slides, how many have been independently audited?
Yeah, so that's a very good question because arkworks has a somewhat long history over the past 4 years in various iterations, and various snapshots of those libraries at various points in time have been audited. I think the latest code base has not yet been audited, though I think we're gonna go for an audit sometime later this year or maybe early next year. We have a few refactors in progress that we want to get out of the way before we audit. I think at that point it'll be more stable.
Okay, great. Any other questions? Yes.
So Planck is not there yet, or
So-
there's a plan, or you?
So actually, Planck, not from, I guess, our group at Berkeley, but there's been a number of implementations from industry folks, such as the ZK Garage folks, the Espresso Systems folks, Findora folks. There's like 3 different Planck implementations, all relying on arkworks. And Mina folks also, yeah.
So it's in the library, you can use it.
So you can use, for example, the arkworks curves in any of these in any of these proof systems.
But you have to depend on their libraries.
Yeah.
Not like Graph 16, you only can depend on arkworks.
I mean, it all, I guess, they all use arkworks libraries, but yeah, you would have to use their code base. We might, once their code base is more stable, maybe depending on whether they want to also move it into the arkworks organization, but it depends on the authors and what they want to do.
I understand. Thank you.
Any other questions? Okay, we have one more.
Yeah, it's maybe more a comment than a question because it came up. So I worked for IOG and I made the job advert before. So I also want to say that we are kind of part of the ZK Garage. And so specifically what we rely on arkworks is their polynomial commitment interface. So we're building on top of that. So when you showed like replacing KCG with IPA commitments, you can do the same thing for the ZK Garage Planck. And I personally would be very interested in kind of integrating it into the arkworks ecosystem and also maybe understand what the governance model is, like what would it exactly take to do that and what do we commit to and vice versa, what is the relationship? I think
that's a good question.
That would be very interesting. Like maybe the next presentation you give, like maybe make that clearer. I think that would be
No, yeah,
cool.
for sure. It's a good question. We're sort of just beginning to think about those questions. No, yeah, we're just beginning to think about and figure those things out. Yeah, it's finally becoming big enough that these questions become relevant.
All right, I think we're at time. Let's thank Pratish again.
Thank you, everyone.
Now we move to the second talk in this session, which is Decentralized Private Computation on Aleo. And the talk will be given by Howard Wu.
Okay, hi everyone. My name is Howard and I'm a co-founder of Aleo. For those of you who don't know, Aleo was born out of a paper called Zexy. Between my co-authors and I a few years ago, we wrote this paper, which stands for Zero Knowledge Executions. It was published at Oakland and introduced a protocol that extends zero cache to support general purpose applications. Given that this talk is already public, instead today I'm going to introduce a popular model for decentralized ledgers called the account model and show some of the fundamental challenges that we faced in terms of extending it to support privacy, and lastly show how we used Zexy and integrated it to enable private computations in a ledger. So let's begin. Today decentralized ledgers have spawned a ton of new applications. For developers, these platforms unlock new ways of facilitating trade and finance, identity and authentication, data storage, gaming and art, and the movement of these assets across these platforms. However, decentralized ledgers also come with some significant limitations. Now, before I dive into those, I think it's important that we first take a step back and look at how these decentralized ledgers work under the hood. So, typically a decentralized ledger works by, well, verifying and confirming each transaction via re-execution. And when you take a look at how this works, first, users will submit a transaction, which is composed of the application, the input, and a signature. The user then broadcasts that transaction to the network, and nodes re-execute that computation. In fact, every node re-executes that computation in order to verify that it is correct. In the case that that computation is correct, well, and the signature is also valid, then the state for the application is updated. And as you can see, there is a lot of re-executions going on here. So let me walk you through some of the limitations with this approach for ledger re-executions. First, ledger re-executions limit scalability. And what I mean by that is that every transaction needs to be rerun by every node in the network in order to be verified and confirmed on the ledger. Now, to give you just a quick heuristic, say you have a network that has 3,000 nodes, and let's say each block contains roughly 5 seconds worth of computations in it. Well, the math adds up to about 15,000 seconds or 4 hours of re-execution per block. As you can imagine, this is, well, incredibly wasteful. Second, ledger re-executions limit privacy. The issue is that each transaction reveals a ton of information about the user and the program that's being run. Namely, it reveals what program was executed, what was the input data to the program, the output data, and who called that program. And notice that everyone will be able to see this for all time, since these transactions are stored permanently on the ledger. So in this talk, we're going to address how we resolve these issues and focus primarily on how our system enables privacy for programs in our ledger. And so we present Aleo. Aleo stands for Autonomous Ledger Executions Off-Chain. Aleo is a decentralized ledger that enables users to execute programs off-chain and finalize state on-chain. In terms of our ledger, we provide several properties. The first is that we achieve scalability, meaning thousands of transactions can be verified and included in each block without re-executions. We also preserve privacy, meaning the resulting transactions reveal no information about off-chain computations. And of course, we have succinctness, meaning the resulting transactions are small in size and fast to verify. Concretely, for reasonable parameter sizes, we get transactions that are approximately a kilobyte in size and can be verified in less than 50 milliseconds. Now, our programs also provide us with several properties. And in terms of the functionality, one of the things that we achieve here is, well, arbitrary user-defined programs. And not only that, but also that we provide isolation for malicious programs from honest ones. And lastly, we enable program functions to communicate with one another in a secure manner. Now, to see how we arrived at our design, let's start by analyzing a popular framework for writing decentralized applications called the account model. So in the account model, a shared global state is typically managed by a decentralized ledger. And to perform a state transition, users sign a transaction, producing a request to execute a program with the given input fields. Now, once the transaction has been verified and confirmed into the next block by the ledger, the account updates its internal state, and it transitions from the previous state to the next state of the program. The intuition here is that users invoke programs with inputs via transactions, and ledgers update their internal state based on the outcomes of those executions. Naturally, a major benefit of this design is its simplicity, because programs contain shared global state, and so it's easy for developers to coordinate complex tasks between multiple parties. However, because complex tasks can be time-consuming, well, large queues of unconfirmed transactions can build, and this would cause significant spikes in network fees to occur. For those who are familiar with something like an Ethereum smart contract platform, something like what CryptoKitties has caused a lot of public attention in terms of having these gas prices for transactions that are quite high. And finally, these transactions reveal their contents to everyone on the network. And this means that the sender and receiver, along with the program inputs, the outputs, and the state are all publicly known. So the question is, how can we redesign the ledger to minimize re-executions and maximize privacy? Well, the solution, of course, is to sprinkle some ZK SNARKs on it. Well, the reality is that it's almost there, but let's extend this account model we just showed and see where we land. So let's take an attempt. We take our inspiration from smart contracts, and we say, can we construct private smart contracts? Well, we can start by committing to the value in the transaction. We can encrypt the data that's contained in this transaction and provide a zero-knowledge proof that can attest to the integrity of each state transition in this transaction. In addition, we can store on the decentralized ledger commitments to that balance, the code for each program as a predicate, and the ciphertext of each program's state. Now, with this approach, transactions can now hide their inputs and accounts can hide the program's state. But we want to prove knowledge about this previous account state while also checking that the new state transition is well-formed based on the input values for this transaction. And so the question is, how do we do that? Let's try to formalize this notion with a high-level statement. And so given a transaction that is of this format, we can say, well, we have to provide what the current code is as a predicate, and we also have to declare what the state is on the ledger. From there, we want to claim that this is the new state of this program on the ledger, and we want to check the following things. One, that value is conserved, as fundamentally it would be a problem if we were minting value out of thin air in this transaction. And two, we want to check that the predicate is satisfied on public inputs which contain the previous state, the next state, and the contents of the transaction.
In addition, the user provides private inputs which contain the plaintext data and storage of the previous state, the plaintext value and data of the transaction, and their private key. Seems reasonable, right? Well, it turns out there's some problems. Why doesn't this work? Well, for one, this approach doesn't support concurrent access to programs' state. And what do I mean by that? Well, say a user broadcasts a transaction that updates program A, and if another user came at the same time and tried to update program A, user 2 here would have produced a transaction that was based on old state. And the ledger would reject the second transaction, which is not great. And so we want to do better on this front. A second problem naturally with this design is that there is no privacy in this account model. And so when user 1 here updates program A, well, everyone on the network will be able to see that user 1 made this update. And this will apply for every subsequent user in this network as well. And frankly, it'll be very easy for everyone to retrace every one of these steps from users in this program, given that this history is now stored permanently on the ledger. So if we analyze the properties that we just designed from this strawman construction, first it's clear that this design is technically more scalable on-chain. And in a moment we'll see what the impacts were off-chain. But the rationale here is that as computations are now predicates that can be executed with a succinct zero-knowledge proof, we no longer need ledger re-executions in this design. Second, we achieve data privacy as we commit to the value and encrypt data and storage in our model. And third, however, as the account model relies on addresses to index into global state, it's a fundamental property and fundamental design decision in that architecture, so we unfortunately can't encrypt the address for each account under anything. It means you can immediately detect which applications a peer has used in the past if you interact with them once on this ledger. And fourth, updating state requires consuming the entire program state. And so for large applications that are producing a proof attesting to the entire state of a program, this could be quite cost prohibitive. And this would mean that some users might not be able to run a program on a ledger in this design, which is also not great. And lastly, this design clearly does not support concurrency, as we had just shown on the previous slide. So the core problem with our attempt here really is that the entire program state needs to be consumed in order to update it. And so with that, we introduce what we call the record model. In the record model, a decentralized ledger now tracks records for each program in shared global state. What I mean by that is, to perform a state transition, users will generate a transaction, computing zero-knowledge proofs that attest to the state transitions performed for a given execution. Once they broadcast it to the network, it's been verified and confirmed, the program will update itself internally, transitioning from the previous state to the new state of the program. Now, the intuition here is that users consume just the records necessary to execute the program for their context, rather than consuming the entire state of the program. This allows multiple users to interface with the same program at the same time. And in addition, the ledger enforces double spend conditions, meaning no record can be consumed twice by any one user or by two parties trying to consume the same record at any time on the ledger. And so if we go back and take a look at that design that we had previously, in this new model, we now have transactions that assert a new high-level statement. Let's walk through this updated design. First, given the predicate of the program being run and the consumed records of the program, we can now claim a new set of records for this program. And we can then assert, one, again, that value needs to be conserved, as fundamentally it would be a problem if we're minting value out of thin air. Second, we check that the predicate is satisfied on public inputs which contain the consumed records, the newly produced records, and, well, the corresponding fee. In addition, the user provides private inputs which contain the plaintext balance and data of the consumed records, as well as their private key. And so we now see that in this model, we have achieved account privacy since the decentralized ledger indexes global state based on program IDs, not on the addresses corresponding to each account. We also see that the corresponding records are consumed to update a program, and so state updates are efficient. We no longer need to consume the entire program state. And because of that, programs are now updated concurrently without issue. And so this is how we arrived at our design for Aleo. And to instantiate the record model, we sampled curves that enable SNARK-friendly cryptographic primitives. Namely, we sampled a 377-bit curve with embedding degree 12, which we call BLS 12377. This curve is great because it supports fast proof verification in our construction. We also sampled a twisted Edwards curve, which is useful for efficient Peterson hashes and commitments, as well as signatures. Speaking more generally, Edwards BLS 12 here really enables us to design efficient circuit operations. Now, finally, we instantiate our SNARK. And we chose the Marlin proof system, which was published at Eurocrypt 2020. Marlin is great because it requires only a single trusted setup for all programs. From a developer experience perspective, it's much simpler to use a proof system like this because it's easy to then use a single global parameter, sample your proving key and verifying key, and deploy this application to the network for everyone to use with the same assumptions. Now, if you'd like to see this work, the good news is it's open source. Aleo is proudly written in Rust. We have about 40+ contributors and 65,000 lines of code at the moment. You can find us on GitHub. The URL is github.com/aleohq. And if you'd like to learn more about us, you can find us at aleo.org. Lastly, I'd like to say thanks. We're hiring, and I'll be at the coffee break after this if you'd like to chat. Thank you very much for your time and attention.
Questions?
So you picked an example of a network with 3,000 nodes, and we're talking about this being in, but if one transaction involved a single variable-based scalar multiplication, that's 4,000 constraints in R1CS. And so that means you're actually spending more CPU time in total than that 3,000 network, than that network with 3,000 nodes, ignoring the bandwidth.
Yeah, no, it's a fair point that you're making. So in our model, because executions are happening off-chain, that variable-based MSM would technically occur once for the actual user who's executing the program. Once that program has been executed, there's now a proof, that proof which goes onto the network for everyone to check. So unless the actual verification algorithm requires variable-based MSM, which then everyone would need to pay, they technically wouldn't need to pay that cost here to verify.
So yeah, my comment was a bit artificial. It's just saying that the total CPU time,
including
the user and everything else. But yeah, okay.
Yeah, in the kind of straw man construction, if you were to use the account model today and re-execute, that variable-based MSM ends up being incredibly expensive, in part because, well, a network in the traditional account model today simply couldn't scale for that type of variable-based MSM computation. And so when you think about where smart contract platforms are today, if you want to do something as simple, simple from a traditional computing standpoint of linear regression or machine learning, where you just extend the kind of usage a little bit further, frankly, smart contracts can't support that level of expressivity yet, frankly, because of this design choice. Thank you.
Thanks very much for the very interesting talk. I think I probably just missed this. I'm not super familiar with the space. What was the motivation for picking new elliptic curve parameters?
Yeah, it's a great question. So in our particular case, one of the design choices we had was a need for recursion. In this case, a degree or depth 2 recursion. And this is necessary in order for the actual blocks themselves to also be further compacted so that you can have what's called succinct blockchains. But the other aspect of it was that this specific choice of curves is also extremely efficient for circuit operations. So when you go to the twisted Edwards curve and you're writing circuits inside of of that domain, the operations that you typically get are what we call SNARK friendly. So if you want to do hash functions or commitments, PRFs, signature schemes, they end up being far more efficient with new types of instantiations on that domain.
And other curve choices people have made so far just don't work for some reason?
Yeah, so existing choices, there are some that do match, frankly, and can do it, but the main differentiating factor would be performance in that case.
Okay, thanks.
Mm-hmm.
Thanks for the great presentation. I was wondering, one argument against the count model was that there's no concurrency, so if you have a global state, then you won't be able to concurrently update it. So in the program ID model, you said you are consuming records. Are you just dependent on the prover to sequence these records that would be consumed in a program ID? But then if there's a global state, then you're still sort of stuck in the same concurrency, right?
Great question. So in terms of, first off, in terms of single party applications, as you can see, there wouldn't be an issue since you would just update that state yourself. In the peer-to-peer model, depending on how you architect it, one way that you would go about doing this is say for a given program, you could say every user has their own record in that program. So when they want to use that program, their program state is based solely on their record, and they can simultaneously run a program because their states are disjoint via this record construction. The other way to think about it is that if you wanted to generalize it not across users but across a program's own context, it could also allocate its resources in a way for its application usage to be disjoint for its users as well.
You gave the example of Uniswap. So in that, you don't necessarily have like a disjuncted state. You're still relying on a global state to update itself.
Yeah, so in the Uniswap case where you're assuming some level of on-chain public visibility, like you need to see what the total, what all the notes are that you can actually swap between are, you would have individual users with their records basically say, here's some amount of tokens for A, and here's some amount of tokens for B, and any parties can basically call these and basically execute. Similar to the Ethereum case, it'd be first come, first served. So whoever gets those reserves first, they make it into the block, and then the ledger enforces that no one else tries to do that from a double spend perspective.
Right, all right, thank you.
Mm-hmm.
Thank you very much for the nice talk. So I haven't read this work before, so sorry if this is a bit of a stupid question, but I'm just wondering, with moving to the record model and trying to still have privacy in on this, is there any issue with the access patterns of what which records arrives and which records is being worked on? Is there like any privacy issues in that setting?
Yeah, so one of the things that I think is important to call out is because we're indexing first off with the program ID, functional privacy isn't necessarily achieved here. What we do get is data privacy. And so because of that, you do get some structure in the sense that what you see as it's going through the mempool into the network and onto the ledger for permanent storage is which applications are popular, what they're, and which ones are frequently used. And so that access is certainly visible. I'd say the other point to make though is that because the actual records themselves are encrypted and committed to, the parties who actually use that and the data associated with that is not revealed. Separate to that is that because the programs themselves can take private inputs for the zero knowledge proof argument that you're making, you can also hide that state as well. It ends up being a choice that the developer gets to make on how much would you like to have public versus private. In this particular talk, the goal was to show the level of privacy that can be achieved with this design, which would basically leak the access patterns for how frequently a program is being used, and you would see, which records commitments are actually being consumed in order to produce state updates. However, the records themselves don't reveal any semantic data themselves.
Right, okay, thank you.
Mm-hmm.
So for the execution of the programs off-chain, you perform the statements inside of the circuits, right? So can you elaborate, like, what level of abstraction do you support? So like, we are parsing from R1CS, and then from there, where do we go?
Yeah, I was actually contemplating whether to include it in the talk or not, but it's a great question. So the way that we ended up designing this to create some abstractions for developers was to say there's really two levels of abstraction that a developer can reason on. For people who want to go much lower level into circuits, we have what's called the AVM opcodes. This is the Aleo virtual machine opcodes, and what we provide are standard, typical, like add, sub, mul, div type of operators, and you can compose assembly-like instructions that basically follow that pattern. Each of those operators themselves is a gadget in R1CS, and so from that perspective, you would be linearly composing a sequence of these R1CS constraints to do that. On a higher level, we also have a programming language called Leo, which looks and feels a lot like TypeScript or Rust. And the goal for that is for traditional web developers who come from JavaScript or whatnot to be able to come into the ecosystem, not know what R1CS is, but write code and have a compiler that will then compile it down to these assembly-like instructions, which then go down to R1CS for actual execution.
Perfect. And for this language, do you provide also optimization?
Yeah, great question. So there's two aspects that we think about. One is an optimizing compiler, and second is a verifying compiler. In terms of the optimizing compiler, oftentimes you can do things like static single assignment, you can do constant propagation, and these notions allow you to immediately reduce the scope of a program, which then helps to reduce the actual size of the circuit and the number of constraints you have to pay when you generate a proof. In terms of the verifying compiler, the other aspect that we look at is how can we formally verify the individual passes that I just talked about on the optimization side to ensure correctness about those programs. Instead of going for a complete verifying compiler whereby the compiler is fully verified, what we do is we actually verify and provide formal verification on individual programs, so you get a one-shot proof per program.
Perfect. Thank you very much.
Yep, of course.
Any other questions, either here or online? Okay, we have one.
Hey, thanks. Maybe a very stupid and naive question, but what's your ideal application?
Great question. There's really three main areas that we find very interesting. One is certainly within the trade and finance space. A lot of people have noticed, there are these decentralized exchanges that are doing public trades. People would also love to see dark pools or different types of private swaps that are happening. On the other front, in terms of gaming, with existing smart contract systems, the problem with gaming is that you can't have a lot of richness in it because of the gas limits. And so say you have these items, like these NFTs, like you have like a furnace and an iron ingot. What people would like to do is to really combine these things and craft like a shield out of it. But the problem is to express that type of rich logic, unfortunately, is too slow and too costly. And so in a model like this where you can do that off-chain, you can now continue to scale that much further. I think one of the last areas that we look at is in terms of identity and authentication, to be able to have almost like a certificate transparency, a log where you can keep a history of these types of roots for trust. From there, you can actually then use that to proof statements about my visit or about my access to this account. And so those are areas that we find very interesting for self-sovereignty then.
All right, super cool. And have you gone as far as to identify conflicting situations with compliance, regulation, stuff like that? Or is that not even something that is considered for now?
It's certainly an open area that we're looking at. I feel like at the moment, given that a lot of regulators have been quite open to seeing what the technology will look like and where it will evolve. One of the things that we're trying to do is to also take a very active stance to showcase different ways or instantiate concretely what this looks like for them so they can actually reason about the trade-offs of designs. And that's at least one aspect that we've engaged in. Otherwise, I think like a lot of folks, we're also looking and hoping for more guidance.
Anyone else? We have 2 minutes if you want to come up with a question. All right, if not, then we can go to the coffee break, and let's thank both speakers again.
Thank you.